is Calculus Section 7.3, looking at something today called a shell method. I've taken this section and divided it into two parts, so today we're just looking at the first part. So yesterday, or last class, what we did was we were taking these rectangles that we had heights that were related to the function that we were wrapping around an axis of revolution, and whenever you spun it, it ended up making a solid disk, or it made some sort of a disc that had a hole cut out in the middle of it, which we call the washer. Well, today what we're looking at is something that's going to create shells. So it's called the shell method. It says it gets its name because it uses cylindrical shells to find the solid's volume. Consider a representative rectangle where W is the rectangle's width. So however thick this little rectangle here, and it's kind of hard to see, but it's a little bit off color, kind of a red rectangle in here. So W is the rectangle's width, H is the rectangle's height, so this distance here, and P is the distance between the rotation of axis and the rectangle's center. So here, if we were to cut this rectangle in half, we're calling that distance here P. Let's see, it says when this rectangle is rotated about the x-axis, it forms a cylindrical shell or tube with thickness W. So now it's created this solid that has a thickness of W. To find the volume of the shell, it says consider two cylinders, one inside the other. The radius for the larger cylinder corresponds to the shell's outer radius, and the radius for the smaller cylinder corresponds with the shell's inner radius. So we're going to think of it as two cylinders. It's just that in order to get the volume of the shell, we would have to take the volume of the two cylinders and basically cut that inside one out. So here it says because P is the average radius for the shell, the formula for the outer radius is P plus W over 2. So if P is in the middle, and then we've got from here to here is W, if we cut that in half and add it to P, it's going to give us that top part of the rectangle. And here, if we take it and subtract it, it's going to give us the bottom part of the rectangle. So it's basically then giving us the radius for that outside bigger cylinder and then this inside smaller cylinder that we're going to subtract. It says this produces the volume for the entire shell. And again, here it shows to find that volume of the shell, we have to take the volume of the cylinder minus then the volume of that hole that we're cutting out, which here the volume of the cylinder is pi times radius squared times height, minus the volume of the hole, which is pi. This here represents its radius, so radius squared times height. If we were to multiply all of this stuff out, distribute, do all of your like terms, we would end up with 2 pi p hw, which then we could think of as it's 2 pi times the average radius times the height times the thickness. So you can use this formula to find the volume of a solid of revolution. Consider a horizontal rectangle of width delta y. As the plane region is revolved about the line parallel to the x-axis, the rectangle generates a representative shell whose volume is 2 pi p of y h of y delta y. So p of y, it's going to be a function depending on where it is we are along our curve. So as we're moving this rectangle, as we were to take it down, it would become a larger rectangle. And as we brought it up, the rectangle would become smaller because this line slanted like this. Our h of y is going to be how tall or how high that rectangle is, which is going to correspond directly to what that function is. And then our delta y is our thickness of our rectangle. It says you can approximate the volume of the solid by n that should say such shells of thickness delta y, height h of y sub I, and average radius p of y sub I. So then the volume of the solid, if we were to sum all of these rectangles, here all they did was they took that 2 pi out because it's a constant, and again we're summing all of those different rectangles from 1 to n, so n number of rectangles, whether it's 5, 10, or 20. Then here it shows, well, what if that number of rectangles were to go to infinity, and this is different than the notation we had before when we were doing the area, because before when we found area under the curve, we always took the limit as n goes to infinity. This one, delta, is going to 0, meaning that that change in y, or basically the thickness of those rectangles, is going down to nothing. And if you have no thickness, it just becomes that straight line and it fills up the entire thing. We know that taking the limit of the sum is the same as taking the integral. So this here is going to be the formula that we're going to end up using. We're going to be taking 2 pi on the outside this time instead of pi like we did with the disk. So it's 2 pi. We're going to have our limits of integration. This py is basically going to represent how far along we are, either along the x-axis or the y-axis, depending on which way we're rotating, whether it's a horizontal or a vertical revolution. And then this h of y is going to be the height, which is going to end up being whatever our function is. So if it is a function of y, it'll be h of y. If it's a function of x, it'll be h of x. And then here, this dy represents that thickness. So dy if it's a function of y, dx if it's a function of x. So on the back here, it kind of shows again real quick, depending on whether it's a horizontal or vertical axis of rotation, whether or not we are going to be in terms of y or in terms of x. But basically here, so if I have a rectangle that sits like this and it is parallel to a horizontal axis, I'm rotating this way and creating then that shell. The height of it is measured from the y-axis out. So this would have to be an x equals equation to measure from left to right, which is why we're working in h of y. If we are rotating around a vertical axis and our rectangles sit up and are parallel and rotate around, now it's creating a shell that sits up instead of on its side. So the height of that rectangle is from top to bottom, and whenever we're measuring from bottom up, that's going to be your f of x functions. So your y equals, so those are going to be in terms of x's. That here, I believe that is a typo. That should not say h of d. That should say h of x. All right, so first example, we're going to find the volume of the solid revolution formed by revolving the region bounded by y equals x minus x cubed, and the x-axis, get my lights turned back on, there it is, and the x-axis from 0 to 1 about the y-axis. So we are taking and rotating about the y, so we're creating a shell this way. The rectangle sits here. Our distance out from our axis of revolution is just going to be an x. So depending on where this is falling, that's going to be determined by this x value. So if x is 1/2, and here it's from 0 to 1, then the rectangle is going to sit right here, and then that will help also then determine our height. But x is going to represent where we are, so that p of x. Our h of x is the height of this rectangle, and the height of the rectangle is determined by the function itself. So that's why they have here h of x equals x minus x cubed. So for this, because it's a shell, it's going to be a 2 pi. We are integrating. It's in terms of x's, so we need an x to an x, and it's going from 0 to 1. And now we need our p of x times our h of x dx. So p of x is just an x times my h of x, which is x minus x cubed dx. And now it's just a matter of integrating like we did last chapter. We don't have any kind of product rule for integration, so the first thing you're going to have to do is distribute that x to make it 2 pi times the integral from 0 to 1. That's going to become an x squared minus x to the 4th dx. Then we're going to have to integrate each of those terms. So we raise the power by 1 and divide by the power. So we still have the 2 pi. This x squared integrated becomes an x cubed over 3. This y to the 4th integrated becomes a y to the 5th over 5. And we're evaluating from 0 to 1. Then here, if I plug in my upper limit minus my lower limit, my upper limit, 1 cubed over 1 is a third. 1 to the 5th over 5 is 1/5. And then just to show the work for, I could put, but I know that when I plug in my lower limit, I'm just going to end up with a 0 minus a 0. So essentially it's just whatever 1/3 minus 1/5 is, and then times that 2 pi. So 1/3 minus 1/5 is going to give us 2/15. And then if I multiply 2 pi times a 2/15, I'm going to get a 4 pi over 15. And that's the volume that is created by taking this curve and rotating it around the y-axis. All right, and example 2. Example 2, we're flipping it around the other way and doing it about the x-axis. So now, if we're using the shell method, our rectangle is going to sit out on the side, or on its side, parallel to this axis of revolution. Our distance from our axis to revolution this time is measured up the y-axis, so our distance is going to be a y. Our height is going to be determined by this function, which they've already given us this function as an x equals equation. It's x equals e to the negative y squared. So that's going to determine our height. Our integration, since we're doing in terms of y, we need to measure along the y-axis. So it will end up integrating from 0 to 1. And then with the formula, we've got that 2 pi out in front. So it's 2 pi, the integral from 0 to 1. Our p, or our distance from the axis of revolution, which in this case is y, times our height, which here the height is determined by this f of y function, which is e to the negative y squared, and then a dy. And now we're integrating like last chapter again. In order to integrate this one, we're going to have to use a u substitution. If we let u equal that exponent, negative y squared, then du is going to be a negative 2y dy, but I only want a y and a dy, so I need to divide by that negative 2. So it becomes a negative 1/2 du equals y dy. So I still have that 2 pi times the whole thing. This negative 1/2 can come out in front of the integral. Then I'm going to have the integral from, and now the thing is here, I can't go from 0 to 1 because 0 to 1 was whenever I was in terms of y. But now I've turned everything in terms of u, so I actually need to figure out then those new limits. So when u equals that lower limit of 0, if I plug in, I'm sorry, y equals 0. Y was that lower limit of 0. If I plug a 0 in for y and solve, I get that u is also going to equal 0. So my lower limit is still a 0. And then when y equals my upper limit of 1, if I plug in a 1 here, 1 squared is 1, but with a negative, u is going to be a negative 1. So I'm going from 0 to negative 1. This y and dy is a du. This becomes just e to the u. So e to the u du. Now, thing is on here, whenever you're doing your integration, you cannot integrate from a larger number down to a smaller number. It's got to be lower to upper. And the rule that we had in order to switch these things was we could throw a negative out in front. So if we make this 2 pi times a negative 1/2 and then pull a negative outside, we can flip those limits and make it negative 1 to 0. EU du. And now when we go to simplify, this negative and this negative are going to multiply to make a positive. This 2 and this 2 from the 1/2 are going to reduce, and all that we're left with is a pi. And when we integrate e to the u, we're going to get an e to the u, evaluated from negative 1 to 0, which is going to give us a pi e to the 0 minus an e to the negative 1. Well, e to the 0 is just a 1. And e to the negative 1 is like saying a 1 over e, because the negative exponent flips it down to the bottom. So we could leave the answer like this. We could find a common denominator here and make it pi times e minus 1 all over e. Or we could plug it into the calculator and get a decimal approximation, which comes out to 1.9 986. All right. Now, the thing is whenever you guys are doing these problems, sometimes there's things that are different along the way, meaning that sometimes whenever you're doing your axis of revolution, you're actually going to have some space in the middle so that your radius is going to be um, increased or decreased, because if I had taken this and I instead wanted to rotate it around, well, say I wanted to rotate it around the line y equals 1 instead of the line y equals 0. Well, now my distance from revolution here, or axis of revolution, isn't going to be just a y, because y measures up, and I would want to measure down. So in order to do that, I would actually have to take a 1 minus y, because, and here I'll kind of off to the side here, if I said that py equaled 1 minus y, when I plug in y equals 0, because that's where it's going to start, I'm going to get a 1, so I'm going to start right here. When I get to y equals 1/2, I'm going to have 1 minus 1/2, so I've moved to 1/2 here, and by the time I get to y equals 1, which was what our limit of integration here was, then I'm all the way down here at 0, because 1 minus 1 is 0. So you kind of have to play with these and figure out, what is that distance from your axis of revolution going to be? What is that height of the rectangle going to be for each individual situation? So here's your homework. A few more problems than last time, but hopefully they're pretty straightforward. Be sure to practice these so that you have answers and work when it comes time for the homework check.